Hey class, so some people were asking about the third question on the most recent workshop, so I thought I would go ahead and I thought I'd make a video, even though it was already past due. So it's a little bit of a weird problem here, right? We have the situation where we have this piston here that's applying a force and creating pressure within a fluid that's resulting ultimately in that fluid, which we're saying it's mercury, so this is a little bit weird that we have a bunch of mercury flowing out the end of our pipe here, but oh well, we'll go with it. And this mercury is flowing out the end at 8 meters per second through a tube that's open to atmosphere. And in addition to that, there's also this vertical tube that has stationary mercury in it that can be actually used to measure the pressure of the fluid down here at point B based on the height in the fluid. It's a cool little apparatus. And so we're asked, based on the information given, to determine what that height ought to be ultimately down at in the tube based on the pressure at point B. So what we have to do is we need to find first the velocity of the fluid at point A, then the pressure at point A, then the pressure at point B, and ultimately the height. So I'm not going to do all of this for you, but want to give you some pointers. So first of all, for part A, when we're asked to find the speed that it's moving at point A, we can use the information given to us. Here at point C, that's part of the same column of fluid that's flowing out the end of the pipe. So we can consider that at point C, where the cross-sectional area of the pipe is 6 square centimeters, that the fluid's moving at 8 meters per second. And we can actually use the equation of continuity. If you recall, the equation of continuity, when it's looking at mass flow rate, says that it's density times velocity times that cross-sectional area is a constant for a given fluid. So that means that at some other place that's density times its velocity times its cross-sectional area would have to be equal. And since we're going to assume that the mercury, we're only given one set density for it, we're going to assume it's incompressible, which means its density is not going to be changing, then we're given the equation V1 times A1 equals V2 times A2, which means you have a constant volumetric flow rate instead of just a constant mass flow rate. So then we can translate this to looking at points A to point C. So V at point A times the area, the cross-sectional area at point A, is going to be equal to the velocity at point B times the cross-sectional area at point B. And so we can easily find VA is just going to be equal to a ratio of the areas, AB over AA, multiplied by the velocity at point B. And since A is double that of C, oh, I said B this whole time, but we're actually interested in point C. That's whoops. So let's get rid of those B's and act like those were C's the whole time. Now you see that it's not B anymore. Anyway, so the ratio here, AC over AA, is just 1/2, and so the speed in the fluid should be half of what it is at point C, so 4 meters per second. Now for B, we're asked to figure out what the pressure is at point A. And so now we can use Bernoulli's equation because, again, we're going to assume that we have this nice ideal flow. So that means that the pressure at point A plus basically the gravitational potential energy of the fluid, so density times gravity times height at point A, plus the kinetic energy per volume, 1/2 the density times the velocity at point A squared, that should be constant. So that should be the same as what it is at point C. So we'd have the pressure at point C plus rho GHC plus 1/2 rho VC squared. And now here, since the center of our fluid is at a steady height, there's no change in height, these guys just go away. And PA then just becomes equal to PC, oops, clicking on wrong things here, PC, which the pressure for it as it comes out is just atmospheric, so atmospheric pressure plus 1/2 rho VC squared minus 1/2 rho VA squared, and you can find the pressure at point A. The cool thing is this idea of Bernoulli's is what you use for the rest of the problem. For C, you do the same thing. All these A's become C's. You need to find the I keep saying, see, all of these A's become B's because we're looking at point B now. I apologize. So let's erase that, right? So now to find the pressure at point B, it's just going to be equal to atmospheric pressure plus 1/2 rho velocity at point C, which we already know is 8, minus 1/2 rho velocity at point B squared, which we don't know, so we have to use the same continuity idea that we used up here to find the velocity at point B as well. Same exact process there, just taking a ratio. Now this velocity should be larger than 8 since the area is smaller. So that gives you the pressure, and then you can again use Bernoulli's. That pressure is going to result in how far up in the pipe the fluid goes, using the same idea where now you have a stationary fluid and you're basically using the same idea but evaluating from down here to up at the top of the pipe for part D. All right, so if you do it all right, you should be able to get box-worthy answers. Maybe to just help you guys out, just to kind of do your checking. If you do part D correctly, you should find H to be equal to 0.275 meters. So you can check your answer in that way. All right, so I hope that helps. Let me know if you have additional questions.